Hello friends, good morning. In this series of lectures, so far I have explained the basic philosophy of protection system and in different types of relays. So far I have explained overcurrent relay, directional overcurrent relay and differential relay. Next, conventional relay is distance relay. So from today I will start distance relays. Let us start with the definition. These are the relays which operate when the ratio of voltage to current falls below certain predetermined value. Ratio of voltage to current falls below certain predetermined value. So we consider V upon I. Now V upon I is nothing but impedance. So we can say that the relays operate when impedance measured by the relay is less than the set value of the impedance. So this is the operating condition. Now, when we consider the impedance from the relay location up to the fault point, when we measure the impedance, it is the measure of distance from relay location up to the fault point. Therefore, the name is distance relays because impedance is measure of the distance from relay location up to the fault point. Therefore, the name of these relays is distance relays. This is non-unit type of protection. Differential relay was unit type of protection. Therefore, it was not able to provide the backup protection. This is non-unit type of protection, so it can be used as backup protection also. This is the general torque equation of distance relays. T is K1 I square minus K2 V square minus K3. So here I, that is current, is generating the operating torque, voltage is generating the standing torque, and K3 is the spring constant. If we are using electronic type of relay, that is static relay or numerical relay, then this effect will not be there, and the equation will be K1 I square minus K2 V square. So this is general torque equation. Now the characteristic of these distance relays can be plotted on Rx diagram by converting three basic electrical parameters, that is voltage, current, and phase angle between voltage and current into two electrical parameters, that is resistance and reactance. So resistance is V upon I into cos of phi or cos of theta, that is Z cos theta. You can say it is either phi or theta, whatever you want to use notation you can use. And x, that is reactance, is V upon I sin theta, that is Z sin theta. Now Z is R plus Jx. We are plotting the characteristic of distance relay in Rx diagram. R we take along real axis and x we take along the imaginary axis, that is y axis. And magnitude is R square plus x square. Now depending on the characteristic of the relay on Rx diagram, the conventional relay characteristics obtained are classified as number 1, impedance relay, number 2, reactance relay, and number 3, Moore relay. So let us start with the first one, that is impedance relay. First one is impedance relay. We start with the torque equation. T is K1 I square minus K2 V square minus K3. Now let us ignore this spring effect, so K3 will be 0, and consider the balance condition, that is relay is just on the verge of operation. So balance condition is torque is equal to 0. So it is K1 IR square minus K2 VR square, that is equal to 0. So we get square root of K1 upon K2 is equal to VR upon IR is equal to ZR. Here I am replacing I and B by IR and VR respectively, and that represents voltage measured by the relay. Whenever I write BR, that will be voltage measured by the relay. IR is current measured by the relay, and ZR is obviously impedance measured by the relay. So this is the balance condition. Now let us consider this balance condition. VR upon IR is square root of K1 upon K2. Now we can take IR is equal to VR upon square root of K2 upon K1. And if we take voltage along x-axis and current along y-axis, then we get a straight line characteristic from this equation, whose slope will be square root of K2 upon K1. Above this line, it will be operating region or positive torque region. Below this line, it will be restraining region or negative torque region. If we consider the mechanical relay, we can use the terminology of positive torque and negative torque. Otherwise, we have to use the terminology operating region and restraining region. Now here, let us find out the mathematical operating condition. So for operating condition, the current should be higher than voltage. So K1 IR square should be greater than K2 VR square. So we get this equation, and as on this side it is ZR, this constant should also be in terms of impedance. We write this as Zn. The operating condition is ZR is equal, it should be less than Zn, where ZR is called as impedance measured by the relay and Zn is called as impedance setting of the relay. So for further discussion, whenever I represent VR, that will be voltage measured by the relay, IR current measured by the relay, ZR impedance measured by the relay, and Zn is the impedance setting of the relay. Now let us see how the characteristic is there on the Rx diagram. Let us see how is the characteristic in Rx diagram. This is the operating condition. ZR should be less than Zn. We have equation Z square is equal to R square plus X square, where R is resistance, X is reactance. So this represents equation of a circle. So in Rx diagram, the characteristic of impedance relay is a circle with radius is equal to Zn. Zn is impedance setting of the relay. So all the impedance vectors whose tip lie inside this Zn, inside this circle, they cause the operation of the relay. So inside this circle, it will be operating region or positive torque region. Outside this, it will be restraining region or negative torque region. So this condition will be satisfied inside this circle. Now let us check the performance of the relay. That is how this relay behaves for normal condition, for internal fault, and for external fault. Now let us check the performance of impedance relay. So to check the performance of the distance relay means how the relay will behave under normal condition, for internal fault, and for external fault on either side. So to check the performance of all the distance relays, I will consider this standard system. In this system, I have shown two sources at both the ends. Then I have shown three line sections, AB, BC, and CD. I have denoted these sources by S1, S2. Two sources on both the sides, three line sections. Now here sources are at both the sides. Therefore, for all the sections, we require two relays, one at both the ends. So for section AB, these are the relays. Section BC, these are the relays. Section CD, these are the relays. I will consider fault in all the sections. In first section, I will denote the fault as F1. Second section, fault F2. Third section for fault for F3. And I will check the performance of the relay R. R is impedance relay. And if you can see here, this relay is used to protect line section BC. It is used to protect line section BC. So impedance setting Zn of this relay will be impedance of the line, that is ZBC. and that is the impedance setting. In all my further discussions for all the relays, when we have to check the performance, I will take this standard system, and I will always consider the relay at point B to check the performance. Now, whenever we have to check the performance of distance relay, we take the help of Rx diagram. R, that is resistance, we take along x-axis, and X, that is reactance, we take along y-axis. First, we have to locate the relay for which we are checking the performance, and we locate the relay at the origin. So here, relay R is located at point B, so point B will be taken at origin. Then we draw the impedance vectors. Consider BC. So impedance is ZBC. This will consist of resistance RBC and reactance XBC. So let us say this is the impedance BC from this point up to this point. Then this is impedance CD. This is impedance of line AB. Now this does not mean that this line has negative resistance and negative reactance. It simply means this line is before the location of the relay. So first we consider Rx diagram. We locate the relay at the origin. Then we draw the impedance vectors. Impedance vector BC, impedance vector CD, impedance vector BA. This is coming in the third quadrant because this relay, we are locating relay B at origin. Second thing is you have to draw the characteristic of the relay being considered. Here we are using the impedance relay. Impedance relay has characteristic circle with center at origin and radius is equal to Zn. So radius will be ZBC. This is, and with this radius we draw a circle. This will be the characteristic of the impedance relay. This is used to protect line section BC. Third step is you have to locate the faults. F1 is in line AB, we are locating it here. F2 is in line BC, we are locating here. F3 is in line CD, so we are locating here. Now let us check for which faults the relay is operating. For F1, if we observe F1, that is inside this circle, that is in the operating region. So relay is operating for fault F1. That is not desirable because this relay is used to protect line section BC and it is operating for the fault in section AB. So this is the malfunctioning of the relay. For F2, it is the internal fault, it is operating. F3, it is the external fault, it is not operating. So we can say that the relay is operating for the fault in both the direction, above B as well as below B. It means the relay is non-directional. This relay is non-directional. Therefore, it is operating for the fault in opposite direction also. So when we check the performance of this impedance relay or in general impedance relay, we find that the relay operates for the fault in both directions. Therefore, the relay is non-directional. Now, to make this relay directional, we have to use additional element. Additional element will be directional element. So if we use a directional element, I had already explained the characteristic of the directional element. It is a straight line. So this is the characteristic of directional element. About this, it will be positive torque region for the directional element. Now, when we use directional element along with the impedance element, the characteristic will be intersection of characteristic of both the elements. So for directional element, it is above this line. For impedance relay, inside this circle. So if we consider the intersection of these two characteristics, that will be a semicircle. This is semicircle. So with this, we find that the relay is not tripping for fault F1. Therefore, in order to provide the directional feature to the impedance relay, we have to use additional directional element. That is the limitation of impedance relay. In my next class, I will explain the reactance relay and more relay. In this class, I explained in general what is distance relay, what is impedance relay, how is its characteristic in RX diagram, and how we check the performance of distance relay. And here I had explained this with the help by checking the performance of impedance relay. Thank you.